One wheel rolls without rolling on a horizontal plane. The wheel consists of a thin circular ring. All right, there we go. With mass m. I'm just going to call that single m. Ooh, black. Okay. Oh, can I do it like that? Yes. And radius r. There we go. As well as 3 spokes. That is an odd number, which are narrow bars, each with mass m. All right, there we go. The angular speed of the wheel in position 1 is omega 1, angular speed 1. The wheel rolls a quarter turn from position 1 to position 2. Determine the angular speed of the wheel in position 2. So we have, I think it's log 1 and position 2. Okay, so I think there's different ways of approaching this. I'm going to approach this from a conservation of energy. Nope, I'm going to start with blue. Blue. So we have energy potential initial plus, yes, okay, energy kinetic initial equals energy potential final plus energy kinetic final. And you might be thinking, what? This is rolling across a, horizontal. There's no horizontal change here. So why are you using energy potential? Well, if you look at it, this entire thing is the same. Ring, check. Upright, check. Little thing going horizontal to the right, check. But the difference here is this bar goes to there. And I know it's not really that way because it's rotating. It's actually this bar that rotates down. But they're all the same, and I can kind of divorce myself from reality here. So reality is not important. So I'm going to say this bar moves to there. And that's going to give us a change in potential energy because everything else is the same. It's just as if that bar fell basically r over 2, radius over 2. And so what I'm going to do then, rewrite this briefly. I'm going to say energy potential, change in energy potential equals change, that is a terrible delta. There we go. Energy kinetic. And this is rotational, but it's all in joules, so I can kind of mix and match, but I do have to be careful what's going on here. So I'm going to say energy potential will be mass times gravity times height, where I know that this mass is the bar. Gravity is just 9.81, and then height was going to be r over 2. And then change in energy kinetic will be 1/2 I, moment of inertia, omega, I'm going to call final squared minus 1/2 I omega initial squared. Okay, seems reasonable. So from here then, we need to find, so this moment of inertia, that is due solely to the geometry of the wheel. And the geometry of the wheel doesn't change, it's just the position of the wheel changes. So the moment of inertia for the wheel isn't going to change. So one of the things I want to solve for here, actually I'm going to simplify this slightly. How did I get green? Did I always have green? That's okay. And then we'll do omega final squared minus omega initial squared, where this omega final is what we're looking for. Omega initial, unknown. And now we want the moments of inertia. So a moment of inertia will just be the sum of all the individual moments of inertia. And so we have 4 objects here. We have a thin loop, which is going to be the same as a particle. So one wheel rolls, we have a thin circular ring, and then we have narrow bars that are being rotated about the center point right there. So I'm going to say for the thin metal ring, I know that's going to be 1/2 mr squared. I just know that off the top of my head. Things you learn in life, I suppose. And then we'll look up the moment of inertia for the bar. Bump, bump, bump. Rod of length L. That looks like what we got. Thin rod. Yes. Does it have to be thin? Infinitely thin, but rigid. Excellent. 1/3 ml squared, where the L is the length of the rod. In this case, it's a spoke, so that length is going to be r. So 1/3 mr squared. Oh, I probably should check loop real quick. Thin circular loop, 1/2 mr squared. So I was correct on. So coming back here, we have plus, there'll be 3 bars. Each will be 1/3 mr squared. They used L, but L and R are the same in this situation. Nope, I already used purple. Don't want to cause undue confusion. I'm already confusing enough. So click, clack. I'll multiply this by 2 over 2 just for a common denominator. And then we have 3 halves mr squared. Okay? So now I'm going to plug this in. I'm also going to replace this h here with r over 2. The reason I do that is I'm looking at how far this bar fell. So if I look at center of mass, it's about there, at horizontal. And the center of mass then will be half of the radius of the circle at that point. So that's going to be r over 2. So rewrite everything. Maybe, there we go. So we mg h over 2. And m is the mass of each of the individual bars plus the circle loop. Not together, but each individual. There's a total of 4 masses involved. So we have 3 halves. So we have, wait a sec, look up here. This is the equation we're looking at. So we have 1/2 times 3 halves mr squared times final omega squared minus initial omega squared. Okay? Doing some simplifying. Change colors to show the canceling. Cancel, cancel. Cancel, cancel. Mass is now irrelevant, which is interesting. So then we have, is that 2/3? Maybe. Feels weird. Okay, I'm going to go with this. 2/3 g over r. So g times 2/3 over r minus plus omega naught squared will equal omega final, where omega is angular speed, and therefore omega final will be 2/3 g over r plus your initial angular speed quantity square rooted. Okay, so backtracking, kind of look at what we did real quick. So all we did here was conservation of energy. Initial kinetic energy plus initial potential energy equals final potential energy plus final kinetic energy. And I said that the only potential energy change was this one bar here falling to that point. Not realistic because it's rotating, but it should give you the same idea here. And I want to do it with energy kinetic because the motion of this thing is going to be kind of difficult to find because it's going to speed up until it gets to something that looks like this. And then it's going to slow down. It's going to be kind of whoop, whoop, whoop. And finding that sort of periodic motion can be challenging, which is why it's easier to look at this just as a conservation of energy point of view. And then we also had the kinetic energy equivalent of 1/2 mv squared, which is 1/2 I omega squared. So I hope that helped, and I will see you next time.